Welcome to this presentation on the calculus. We're reviewing integration. We're going to recap standard forms, we're going to solve indefinite integrals, differential equations and definite integrals. The process of integration reverses differentiation, a process we've come across before. So if we were given a function of y equals to x cubed and we're asked to differentiate it, we get an expression dy by dx is equal to 3x squared from standard differential tables. If we now try and integrate dy by dx of the 3x squared term, we will get back to the original function of y equals to x cubed, and that's using standard integral tables as shown below. Just looking at the nomenclature associated with integration, this elongated s symbol actually means the integral of, and the y dx here is the integral of y with respect to x, the dx meaning with respect to. So in this case y has been shown as a function of x, it's shown as 4x, so we're integrating 4x with respect to x, and our solution here is 2x squared plus c. Only functions of x can be integrated with respect to x, so we must make sure we have consistent variables inside our integral. So for example, we can integrate 2x with respect to x, that is a coherent calculation. We could integrate 3u squared with respect to u, again that's a coherent calculation. So only functions of x can be integrated with respect to x, or a function of u integrated with respect to u. Okay, our standard of table integrals here. You're probably familiar with the standard table of differentials. This is the reverse tables. In this column we have the integrand, the function of x, and then the solution, the integral in this column. We take our first format, the ax to the n, the polynomial, integrated with respect to x will give us a solution of ax to the n plus 1 over n plus 1 plus c. I'll talk about the plus c in a moment. This solution works for all values of n except when n is equal to minus 1. Our second type of integrand, sin ax, integrated with respect to x, integrates to minus cos ax over a plus c. Cos ax, integrated with respect to x, goes to sin ax over a plus c. Sec squared ax, integrated with respect to x, goes to tan ax over a plus c. E to the ax, the exponential, integrated with respect to x, goes to 1 upon a times e to the ax plus c, or e to the ax over a plus c. 1 upon x, integrated with respect to x, or x to the minus 1, integrated with respect to x, goes to ln x plus c. And finally, the first differential of x over the function of x integrates to ln function of x plus c. We will also use the laws of indices in this work to simplify to standard form. If we consider the arbitrary constant of integration in the previous table, if we integrate the function 2x with respect to x from the previous standard integral table, we get x squared plus c. The plus c is essential. If we do not add the plus c to our solution, we get incorrect solutions. So we must add the plus c when we integrate a function without limits. I'm going to illustrate why we need the plus c in our solutions. If we were given the function y equals to x cubed minus 3 divided by x squared plus an x minus 5, if I write that in standard form of ax to the n, that would be y is equal to 1x cubed minus 3x to the minus 2, bringing the x to the 2 to the top line using laws of indices, plus 1x to the 1 minus 5x to the 0. Don't forget, anything to the power of 0 is 1, so I've still got minus 5 at the end, even though I've written it as minus 5x to the 0. If we now use our standard differential tables and differentiate ax to the n, we get an x to the n minus 1. I put the detailed solutions there, but I'll jump to the final line here. Dy by dx would be, from our standard derivative tables, 3x squared plus 6x to the minus 3 plus 1. I'll let you look at the above line at your leisure. So continue with the illustration. I just repeated this line, dy by dx equals to 3x squared plus 6x to the minus 3 plus 1. We've got that by differentiating. Now if we want to reverse the process, we need to integrate. Integration should take us back to the original y function. So to do that we have to rearrange the equation. So I multiply both sides by dx to get the dx on the right hand side, and then I put my integral sign in front of my terms to integrate. Notice I've got a bracket around the right hand side terms. Now if I again write them in the form of ax to the n to make them easy to integrate in terms of the integrand table, I will get now on the left hand side the integral of 1y to the 0, that's an ax to the n format, integrated with respect to y, and on the right hand side I get the integral of 3x squared plus 6x to the minus 3 plus 1x to the 0. Again I'm using the x to the 0 being a value of 1, so I haven't affected the actual integral here. And I'm going to integrate with respect to x here. So from our standard integrand tables, when I integrate ax to the n with respect to x, I get a form of ax to the n plus 1 over n plus 1 plus my c. And I can use this as long as my n doesn't equal to minus 1, and that's true in this case. So again, I've laboured a solution on these first two lines here, but I'm going to go straight to the final solution. What you find now is we get y is equal to x cubed minus 3x squared plus x, but we've lost the original constant. The original minus 5 was missing, and that's why we need to put the plus c into the equation. Okay, there are ways of finding the plus c which we'll look at later on, but that is the solution for this problem. The minus 5 is missing, so the plus c is trying to account for that. In example 1, we're just going to show how to use various forms of the standard integral table to solve integration problems. So we're given the integral, and there are four functions here. We've got 4x cubed plus x squared minus 10x over 5 plus sine x plus 3 over x. All have to be integrated with respect to x. So initially it doesn't look like they're in standard form, but if we think about it in a bit more detail, they actually are. If I now consider the integral again, the 4x cubed is standard form, ax to the n, and I actually get x squared upon 5 and take away 10x upon 5. The 5 is a common denominator for those two terms, so I put them into partial fractions there. The plus sine x is a standard form, and if I bring the x to the top line using our indices, a negative index here, I get 3x to the minus 1, and that becomes a standard form. So now when I look at my functions and I'm integrating, I've got 4x cubed standard form, x squared upon 5 is standard form, 10 divided by 5 is 2, so minus 2x is now standard form, plus my sine x standard form, plus 3x to the minus 1. All standard form integrated with respect to x. These are in the tables, the ax to the n, the sine ax and the x to the minus 1 are all in the tables. So when I look at my solutions, integrating through 4x cubed, integrated becomes 4x to the 4 upon 4. The x squared upon 5 becomes x to the 3 upon 3 times 5. The minus 2x becomes minus 2x to the 2 upon 2. The plus sine 1x becomes minus cos 1x here, and the 3x to the minus 1 becomes 3 times ln x. I'll let you look at those with the standard forms. We then simply add the c in this case for the constant of integration. Just tidying that last expression up, we get x to the 4, x to the 3 upon 15 minus x squared minus cos x plus 3 ln x plus c as our solution. All standard forms. Okay, example 2 here, we're asked to solve again an indefinite integral. This integral shown here, integral of x squared minus 10x plus 6 all divided by 2x plus a cos x, and then take away a 3 upon x plus 2, all integrated with respect to x. So looking at my standard forms here, if I divide the x squared by 2x, I will get x upon 2, which is standard form. If I divide my minus 10x by 2x, I get minus 5, standard form. If I divide the 6 by the 2x, I get 3x to the minus 1, bringing the x to the top line here, and again that's standard form. The plus cos x is standard form, and so is the minus 3 upon x plus 2, all standard form, and all integrated with respect to x. If I look at my standard tables, when I integrate x upon 2, I get x squared upon 4. I'll let you think these through. If I integrate minus 5, I get minus 5x. If I integrate the 3x to the minus 1, notice I have to use this format down here. I get 3 times ln x. Integrating the cos x, I will get the sin x function. And this last one is actually of this format where the numerator is first differential of denominator. If you differentiate the denominator, you get 1, and on the top of effect you got 3 times 1. So looking at the solution format, I simply get minus 3 ln x plus 2 in brackets. And then I add my plus c for the final solution. Okay, we've talked about adding the constant of integration to all our solutions. What if we actually want to find out its numerical value? Well, for that we need to be given some boundary conditions, and you'll see in the examples we're going to look at now, they will give us boundary conditions, and that will allow us to solve for the constant of integration c. Okay, example 3 here, we're asked to integrate the expression dy by dx is equal to x squared. That's called a differential equation, a first order differential equation, and we're going to solve it using integration. We're given 2 conditions here, some boundary conditions here, that when x equals to 2, y is equal to 3. That's our boundary condition. We're asked to find both the general solution, that's with the plus c in the solution, and the particular solution, that's when we've evaluated the plus c and it becomes a numerical value. So let's go through that process. So given that dy by dx is equal to the function x squared, I'm going to rearrange that by multiplying both sides by dx and integrating. So I integrate on the left hand side 1 with respect to dy, and on the right hand side I've got integration of the x squared with respect to dx. So both standard forms of ax to the n, and if you look in your tables, that will give you y equals to x to the 3 upon 3 plus the c from our standard integral tables. Okay, example 3 here, I've just repeated the general solution y equals x is 3 upon 3 plus c for convenience. What we're going to do now is try and find the particular solution, and to do that we need the boundary condition given in the question. In the question it says that x is equal to 2 and y is equal to 3, sometimes written as 2 comma 3 in brackets, and that relates to a point on the curve we're trying to find. So all we do now is put the value of x and y into the general solution. So on the left hand side I put the value of 3 for the y, and on the right hand side I put the value of 2 for the x. I just simply work this out. It's just a rearrangement, a transposition here. I take 8 upon 3 from both sides, so I get c is equal to 3, take away 2 in 2/3, that's my 8 divided by 3. That gives me a constant of 1/3. So my particular solution in this case is going to be y is equal to x to the 3 upon 3, now plus my c, which is 1 upon 3. All I've done in the last line is factorise on the third. Okay, exercise 1 here, solve a differential equation, dy by dx is equal to x squared plus 3. We're asked to calculate the constant of integration, the c value. We're given that the curve passes through a point 3, 8, that's x, y. That will allow us to work out our constant c, and so our particular solution. We're also asking this question to determine the value of y when t is equal to 5. So once we've found our particular solution, it's saying we need to use it. Okay, so given dy by dx is equal to x squared plus 3, we multiply both sides by dx, and we integrate both sides to solve this. Okay, the left side is integral of dy, and the right side of integral of x squared plus 3, all with respect to x. So our solution will be y is equal to x squared integrates to x to 3 upon 3, and 3 integrates to plus 3x plus c. We now have our general solution. Exercise 1 continued. I just repeated the general solution for convenience. I'm going to now impose the boundary condition into the general solution. We're given that x is equal to 3 and y is equal to 8. So all I do now is put the y is equal to 8 on the left hand side and the x equal to 3. Wherever I see have an x, I put a value of 3 into the equation, and I just simply evaluate the equation. Again, a little bit of rearrangement here. I find my constant c is equal to minus 10. So my particular solution here, y is equal to x to 3 upon 3 plus 3x, and then minus 10. That's the particular solution. Exercise 1. So the final part of the question now is to use the particular solution we've derived, the y equals to x cubed upon 3 plus 3x minus 10, and simply put the value of x equal to 5 into the right hand side where we see an x. So y is x cubed upon 3, that's 5 cubed upon 3, plus 3 times x, that's 3 times 5, take away 10. We do the arithmetic on this, we find that the value of y is equal to 46 2/3. Exercise 2 here is a similar process to that of exercise 1, but the notation is changed. Instead of having dy by dx equals some function of x, we've got dp by dt is some function of t, and also the function of t is not in a standard form. It's actually 3 minus t all squared, so we'll have to expand the brackets in a moment. We've got to find a particular solution because they've given us the values of p and t. We've got a boundary condition basically given to us. So in this case, our dp by dt is actually 3 minus t all squared, and don't forget that is 3 minus t times 3 minus t, so we've got this binomial bracket to expand. So multiplying out the bracket, we will get 9 minus 3t plus t squared. And if we simplify that, it becomes 9 minus 6t plus t squared. That now is standard form. So now I can integrate the left-hand side and integrate the right-hand side. Note I've multiplied by dt first of all. So on the left-hand side, integrating dp, I get p. On the right-hand side, I get the integral of 9 will go to 9t. The integral of minus 6t will go to minus 6 t squared upon 2, these are all standard forms, and plus the integral of t squared goes to t cubed upon 3, and of course I have my constant of integration. If I tidy that up slightly, my general solution p is equal to 9t minus 3t squared of 6 divided by 2 gives me 3, plus my t cubed upon 3 plus my c. Continuing exercise 2 here, I've repeated my general solution for convenience here. We're given the boundary condition in the question when t is equal to 2 and p is equal to 3. That's like my kind of x and y conditions. So all I do now is put the value of p, 3 in this case, on the left hand side for the p, and I put the value of t is equal to 2 wherever I see a t in the equation on the right hand side. Again, just solving that with the arithmetic, I end up with c is equal to minus 5 2/3. I'll let you take your time looking at the arithmetic there. So our particular solution we end up with is y is equal to the 9t minus 3t squared plus t cubed upon 3, and then minus 5 2/3. Okay, exercise 3 here, we're asked to solve the differential equation dy by dx is equal to 7 plus 3x squared divided by 5, take away 2x cubed. We're asked to find the constant of integration, and knowing that the curved path is through point 3, 2, x, y, and state the particular solution. So again, as before, we write in my equation, I get dy by dx is equal to the function given, but I need to multiply both sides throughout by the dx, and then integrate both sides to solve the differential equation. Okay, it's all standard form. On the left hand side, the dy integrates to y. On the right hand side, the 7 integrates to 7x, plus 3x squared upon 5 integrates to 3x to 3 upon 3 times 5 is 15, and then the minus 2x cubed integrates to minus 2x to the 4 upon 4, and I add my constant of integration. Just tidying that line up, I get y is equal to 7x plus x cubed upon 5 minus x to the 4 upon 2 plus my c, and all I've done for the general solution is write the y in terms of decimals. That could be 7x plus 0.2x cubed minus 0.5 x to the 4 plus c. Continuing exercise 3 here, I've just repeated the general solution for convenience for y there. We're now going to find the constant c. We know from the question the boundary condition is 3, 2, x is 3 and y is 2, and all we do now is put those values into the general solution. So on the left hand side I get the y of 2, and on the right hand side, wherever I see an x, I put the value of 3 into the equation. The rest of it is just arithmetic. That ends up with the constant c being 16.2, so my particular solution in this case is y is equal to 7x plus 0.2x cubed minus 0.5x to the 4 plus 16.1. I'll leave you with a couple of exercises to have a look at. Exercise 4 and 5, and the solutions are given in both cases. In exercise 4, notation again is changed. Instead of dy by dx, we've got dy by d theta, and so we've got a function in terms of theta, but again they're all standard forms. 12 cos 3x is standard form, 6 theta to the minus 1. I would suggest you use there that standard form, and a constant of course is standard form. So all standard form functions in both cases. Again, with exercise 5, I think I might bring the x squared to the top line to make x to the minus 2 before I start my integration. Okay, up to now we've only analysed what are known as indefinite integrals, in other words integral of x to the n with respect to x. Indefinite integrals always have a plus c in their solution when we initially integrate them. We can find the c later on, but initially they have a plus c in them. What we're going to look at now are definite integrals. Slightly different format here. This is a definite integral, the integral of x to the n with respect to x, but now between the limits of a and b, where a and b are known as the limits of integration, a being the lower limit of integration and b being the upper limit of integration. Okay, example 4 here, we're going to solve the definite integral of y is equal to the integral of x to the 4 with respect to x between the limits of 1 and 2. So the x to the 4 is a standard form in our tables. It's ax to the n format. When we integrate that, we will get x to the 5 upon 5 plus my constant c. This will be integrated between the limits of 2 and 1. Okay, so those are my limits. Notice the format I've used here with the limits at the back of a square bracket, and I would encourage you to keep the same format. Now I impose my limits. The upper limit always goes in first, so I put the value of 2 where I get an x, so x to the 5 is 2 to the 5 divided by 5 plus my c, and I always take away my lower limit. In this case the lower limit is 1 to the power of 5, that's x to the power of 5 divided by 5 plus my c. 2 to the power of 5 is 32, so divided by 5 plus c is in my first bracket, and I'm taking away 1 divided by 5 is 0.2 plus my c. And what you notice here is when you account for the negative outside of the second bracket, it changes the sign of the terms inside. So I get a negative 0.2, and a negative times a positive, I get a negative c. And what you notice here is that the c's cancel. The plus c cancel with the minus c. So the final answer is simply 6.2 with no c. And that is true for all definite integrals. The constant c's always disappear. So just reviewing example 4 here again, this is a solution for convenience. The square brackets are used to mean the integration of each term has been completed, so we need to keep the idea of the square brackets in these solutions. They do mean something, and the limits are always put at the back of the square brackets. Okay, we put the limits in, the upper limit always goes in first and the lower limit all goes in second, and we take the lower limit from the upper limit value. The constant is c, as we said before, has cancelled out. So whenever you're solving a definite integral, you never need to add the constant c at the end of the equation. It will always cancel. So we can omit the constant c, even though it's shown in our standard tables. Example 5 here, we're asked to solve another definite integral. Y is equal to the integral of x cubed with respect to x between the limits of 4 and 6. X cubed is a standard form. Integrating x cubed with respect to x, we get x to the 4 upon 4 between the limits of 4 and 6. Again, notice the square brackets used here and the limits at the back of the brackets. What we do now is impose the upper limit into the equation, so x to the 4 is now 6 to the power of 4 divided by the 4, and we take away the lower limit, which in this case is 4, so x to the 4 now becomes 4 to the 4 divided by the 4. So So finally, calculating the value of y is equal to 324 for the first bracket, take away 64 for the second bracket, so the final answer is 260. Just to show you graphically what example 5 is actually doing, when we are integrating, we are actually finding areas under curves. So when we're asked to integrate x cubed with respect to x between the limits of 4 and 6, this is the x cubed function plotted for us, and what we're doing is finding the area between the limits of 4 and 6 under that curve. That's what the integration process actually does. It finds the shaded area, in this case, under the graph. I would encourage you to have an attempt at some exercises here. Most of them are standard forms. This first one is x squared, integrate between the limits of 1 and 2, so a definite integral of standard form. The same with question 2, 2x plus 3 is standard form, integrate between the limits of 2 and 3. Question 3 here, definite integral again, standard form inside the bracket, integrate between 0 and 2 in this case. Question 4, again standard form, the 3 terms inside the bracket this time, but all standard form, integrate between the limits of 1 and 2. Question 5 here, expand the bracket first of all. That's not standard form as we look at it, so expand the bracket, multiply both terms in the bracket by x, and then integrate between limits of 1 and 2. And the last question, question 6 here, again definite integral, it says the square root of x here, so make sure you put that into a fractional index of x to the half before you integrate it between the limits of 0 and 2. Thank you for viewing.